how do we do this? The point of this exercise is to do this sort of general case. So in the general case, you can write the classification error as an integral instead of a sum. It used to be a sum, right? When we conditioned on x, this was probability of x is equal to x. So that's one way of writing things. In the more general case, you can write it as an integral. In the continuous case, this is just, let's say, you can write it as px dx if you want. The density of x. And so if you try to minimize this, you would easily argue that you have to minimize this. So you pick f of x such that this is argument over all d. Now d could be still 0, 1 for us, such that this is minimized because this term you can't do anything about. So one thing that I wanted you to do is to calculate this rule, this optimal rule, in this example. So this is an example where we're given x given y as an exponential distribution. And so the whole point is trying to compute the conditional distribution of y given x, given this information, and the marginal distribution of y. Okay. And so this is sort of straightforward if you go back to your probability course. The only difficulty is that one of these random variables is discrete, the other is continuous. So I'm going to do maybe not exactly the exponential, but I'm going to do something in between 2.6 and 2.7. Suppose, for example, you have x given y is normal between, let's say, y and variance 1. Okay, so what this is saying is that if y is 0, this is normal 0, 1. If y is 1, this is normal 1 and 1. Okay, so the first argument here is the mean, the second is the variance. So the variance is the same. So depending on which class you are, so these are sometimes what we call these class conditional. So in specifying what is the distribution of x under each of the two classes. So if you plot, for example, so this is saying that if x is under y0, so if you're generating, so imagine like a generating process, you first sample the label 0, and then you sample a Gaussian with mean 0, standard Gaussian. So that's the distribution of x. So you can represent it with, I'm going to use this notation. So p of x given y equals z, that's the conditional density of x given y equals z, or I'm going to write p naught of x. Okay, so that would be like 1 over root 2 pi e to the negative x squared over 2. Okay. And then we have p of x given y equal 1. I'm going to write it as p1 of x. So these are densities. So it's going to be 1 over root 2 pi. Anyone remembers what this one will be? I'll show you what this is. It's going to be like centered at 1, like a shifted version of the other one. So this is p1 of x. The other one is p naught of x. What would this be? Yeah, x minus 1 squared over 2. Okay. So we have these two. And then I'll also give you the probability of y equals 0, which I'm usually write as this in sequence discussions. And then I also have probability of y equal 1. which I'm going to write as pi1, but you also know that these sum to 1. So this is not necessarily X transformation. Okay, so I have these. So I have the marginal distribution of y given here. And then I have the conditional distribution of x given y given the density. Now the idea is how to compute. Let's say I just need to compute something like this. Probability of y equal 1 given x is equal to x. How do I do this calculation? Bayes rule. So how do you write the Bayes rule? So if it was discrete, you would write probability of x is equal to x given y equal y times the probability of y equal 1 divided by the probability of x is equal to x. So that's the Bayes rule with discrete events. So now what we are going to sort of argue, I'm going to replace this with just the density, y equal 1, and this also with the density. Okay, the density of it. Right. So if you think about this, like working with infinitesimal events, that's what the right formula is for probably y equal 1 given x is equal to x. So we know this. So this one I have here. So what is P of x? The basically marginal density of x. Like this guy. What is that one?
X given by tau probability of y.
Can you say it again?
Probability of x given y equal to 0 and tau probability of y equal to 0 plus.
So that's like the density basically. Density of x given y equal 1 times the probability of y equal 1. So you can do the same thing but with the density. So this is pi, okay, p of 0x. This is p 1 of x, and this is pi 0, and this is pi 1. Okay, so this is really a mixture. So pi 0, pi naught times pi naught pi 1 of pi naught times pi 0 of x, and then pi 1 times pi p1 of x. So it's like a weighted average. Okay, so you just sum these two with the weights, and if the weights are the same, basically you average these two out, you get something like this. Okay, so that's the marginal distribution of x. Ignoring this, so once you like marginalize y, so if you don't know y, that's how the distribution of x looks like. Okay, so these are basic probability ideas. And then we do it here. So any questions so far? Okay, and then you realize that these are also like we have shorthand notations for those. So once you write everything down, you would get, so this goes here. Probability of y equal 1 given x is equal to x is basically pi 1, that's this part, times p of pi 1, p of p1 of x divided by pi naught p of x plus pi 1 p of x. Okay, so you can calculate what this is. But we really don't need the actual, this is doable. You can write it down, it's just a function of x. What we really need is this is like our eta of x. This is the regression function. So the classifier is 1 if eta of x is bigger than 1/2, if you remember. 0 if eta of x is less than 1/2. And since people some people have extensions. I'm not gonna tell you what happens at the boundary, so you hopefully figure it out. But that's the classifier. So I really need to compare this quantity with 1/2. Okay. So if you do eta of x bigger than 1/2, so this is equal to pi1 p1 of x divided by pi0 pi1 of p of x bigger than 1/2. And then you do the algebra. Everything is positive. Do the algebra, what would happen?
pi1 p1 greater than pi0.
Yeah, so if you multiply, we get 1/2 pi naught p naught of x plus 1/2 pi1 p1 of x, and you rearrange. So you get something like 1/2 pi1 of x p1 of x is bigger than. And then these would cancel out, so you get pi1 of x divided by pi0 of x bigger than pi0 divided by pi1. So our classifier tells you, like this does this, 1 if this happens, 0 if the other side happens. Okay, so that's the rule. So this is the region where you classify as 1. Does this look familiar to people? Does this have a name? Ratios. You all know what this P1 x divided by P0 x. Yeah, starts with L. Likelihood ratio. So that's called the likelihood ratio. So really, we can see that classifier is just the likelihood ratio classifier. I would say call it likelihood ratio classifier. For the likelihood ratio, so this is the likelihood ratio. Go back to your set point in this case. And so usually in the context of testing, the hypothesis testing disappears. So you threshold the likelihood ratio. If it's bigger than something, you go for 1. If it's less than something, you go for 0. And so if you do it here, e1 of x divided by pi naught of x. For the Gaussian case, you get 1 root 2 pi e to the negative x minus 1/2 squared divided by 1 over root 2 pi e to the negative x squared over 2. So what would happen here? Sorry. So you get, okay, e to the x squared minus. Right. So then what happens? Let's see. I'm not sure if I'm going to do the calculation correctly, but it's like going to be x plus minus 1/4. Yeah. So you square this, the quadratic terms go away. And then you get negative 2x divided by 2. So you get x, and then, is that correct?
1 by 2.
1 by 2. Where is that?
Instead of 1.
I'm saying like x squared minus 2x plus 1 over 2. Okay, thanks. Good. 1/2. So if I want to compare this to the threshold, so another way of doing it is like, okay, in this case, I'm going to take the log. So log P1 of x, P naught of x has to be bigger than log pi0 over pi1. If pi0 and pi1 are 1/2, then what would this be? 0. So this would be 0 in the balanced case. But if the classes are balanced, phi 0 is equal to phi 1, so log of 1 is 0. And this in this case, it's going to be x minus 1/2. So you really like classify 1 if x is bigger than 1/2, which is very reasonable. Okay. So you're saying if the classes are like that, if I'm bigger than 1/2, I'm from class 1. If I'm less than 1/2, I'm from class 2. And you can see if the classes are unbalanced, then this threshold is going to change. So this is not going to be 0, it's going to be something else. Then you like change the threshold. But the structure of the class is very limited. Okay, so you do this for that exercise, you get like a class for it with exponential, you get something like that. Either you classify if it's bigger than something or less than something, depending on which one is to the other side of the other. Okay, so that's sort of in between. And so this problem, linear discriminant analysis, one of the classic results in like statistical learning, let's say very before like machine learning. It goes back to Fisher. Assuming that these class conditional are Gaussian, now everything is in RD. So you're going to use the negative side. So the mean depends on the class, but let's say you have a covariance matrix sigma. If you want, you can assume it to be identity if it's easier. But it works with general sigma. We assume that like in this setting, we assume we know the distribution, you know mu's, you know sigma, and then you want to show that you go through this argument, you end up, you have like multivariate Gaussian densities, and then you end up with, so the difference times the sigma inverse is this rate vector. So W transpose times X, if it's bigger than C, you say you're in class 1, if it's less than C, you're in class the other one. So in our case, this is basically 1. And this is 1, this is 0. So this W is really 1 in the univariate case. So they just did. Let's say it's 1 if X is bigger than, in this case, 1/2. So C can also determine, C will depend on the ratios of the class conditions. But that's the general idea. Okay. So this is like in the multivariate case, this leads to this idea that this is going to be a hyperplane in RD. So let's say in two-dimensional, if you have a two-dimensional problem, what it's saying is that one of the classes is like maybe this. These are the level sets. The other class is like this. These are the level sets of the density, and the classifier sort of is a line. So classifies to one side as 1, the other side is 0. Sounds good. So do it as an exercise and think about it. And so this is assuming that we know the distribution. So you remember, we started with a very general distribution, joint distribution. First, we assume that we know it. Then this is the optimal classifier. Then you try to like estimate it from data. So these models assume a parametric form. So the ones that we discussed or discussed today as well. Again, we're trying to not impose any parametric structure, but together, so this assumption on the classes, plus this assumption on the conditionals, this specifies a very specific joint distribution for X and Y. One whose marginals of X given Y are Gaussian multivariate, and this is Y. But this is the key. So this might not be true in practice, but if you assume it, then this is the optimal classifier. And in practice, what happens is that you estimate, just to estimate mu1, mu2, and sigma from data. Which is easy to do. Like you have training data, you estimate, you get an estimate of this, you don't have to do that kind of density estimate or the more fancy estimate that we were talking about. We were talking about. just have to estimate a bunch of parameters, which you know how to do. You know how to like estimate the mean just by sample mean of class 0, by sample mean of class 1, and then the sigma you can just pull together everything, and then if the sigma is shared, you can get an estimate of covariance. These are standard things in statistics. And then once you have it, you just add hats here everywhere. So you have the hat here, and then you get the hat there. Then this might be a hat as well. So you get like a plug-in estimator, or a plug-in approximation to that. Okay. Sounds good. No questions anymore about 2.6. So I'm going to use this notation later than like phi 0, phi 1. This is one way of specifying the joint distribution. And not of x, p1 of x. Okay. Okay. So we're back where we left off. So again, we're in the continuous feature case, and we're trying to estimate the regression function. And then we sort of argued that you can like basically extend the idea that we had for estimating this in the discrete case to the continuous case by just replacing these used to be like strict indicators here, xi is equal to x, with like a soft similarity metric, which is often called the kernel. And so these would effectively average for every like test rule x, average y's that are similar, or y's for the samples that have similar xi's to x. And a particular case was this Nadaraya-Watson, so-called Nadaraya-Watson estimator. It's a non-parametric, so-called non-parametric estimator of the regression function, as opposed to, for example, what we did just now, with the parametric approach to estimate things. So you form the similarity matrix as a scale and translation, like translated and scaled version of a mother kernel, this kernel. And so if you have a Gaussian kernel, for example, scaling by edge would change the basically variance, or like the sharpness, if you will. The sharpness of the kernel depends on this edge, which is called the bandwidth. The smaller it is, the sharper it is, the bigger it is, the flatter it is. So, and then you translate it around, okay? Translate this one around, and then you get these similarity matrices. And then you plug this into your formula here, you get an estimate. Okay, so you get, for example, so h's would cancel out. You get kf. Let's say xi minus x times yi divided by h, and then summation of these. So that's what would happen. Okay. And then if you apply this in practice, you can try to think what this is, like bumps on the real line, and then you sum them, but I'm going to skip. So if you apply it, you get things like this. So this is the breast cancer data. We had this diagnosis column, or the other way around, 1 being the line, 9, so on. And I'm predicting based on this radius column using this Nadaraya-Watson with the Gaussian kernel. And you can see, well, stuck again. So if you look at this, the x-axis is these features. So the radius mean. So it goes from, I don't know, we don't have the range, but let's say around, let's say 11, maybe to 20 or something. Right, and then there are a lot of things around the middle, like 15. And so these are the data points. So this is, for example, one data point that has maybe 18 as the radius, and then this is y. Okay, this is 1, this is 0. So you can see some samples have response for like target 1, and these are the x's for that, and then some have 0, and these are the x's for that. And you can see the tricky part is around the middle, that there are things that are both, like if you want to just make classify based on the x, it's hard to tell because it's like, there are these things that are 0, and there are these things that are 1. So you form that regression function, you can see that this is what it does. So it just, this quantity, I'm computing this quantity with the Gaussian kernel and a certain bandwidth, edge, so the plots that you see for different edge, and then I vary the little x. Okay, so if you vary the little x, you'd get these plots. And so you can see as I, so the green one is h equal to 3, and the red one is h equal to 0.25. So it gets more wiggly. But you can see it's like gets a little bit better. So h is equal to 3. It's very smooth, but it's not necessarily quite detecting that boundary chart. As you decrease edge, the black one seems to be quite optimal. It's like smooth and get the boundary right. And then the red one is more wiggly, but it's quite well. And so the way that you classify is that you approximate this regression function, and then you cut it at 1/2. So remember the estimator is f hat of x is 1 if this is bigger than 1/2, 0. Okay, so the critical thing is this line 1/2. So what happens with the green one is that I'm gonna decide everything to the to this side is class 1. With the, for example, black one, I'm going to decide here. Okay, everything to the left, right. You look at, but to this side of the line is class 1. Okay. So the fact that the bandwidth is going to give you a different result tells you that you have to choose the bandwidth somehow. And you can see a smaller bandwidth gets more wiggly. So that's a manifestation of the variance. So the variance of the estimator gets larger. Although the variance is not this wiggle, it's just the variance is if you repeat the experiment many times. So like, this is for one training set. If I had another training set, I would repeat the experiment, I get a different eta. And if you do it again, you get a different eta. And I can look at each particular x, and this is going to vary. This location is going to vary because the next time I get something like that, the next time I get something like that, like that. And so the range of the variability is the variance of the estimator eta hat x. And there's something else called the bias, which is, so there's the variance of eta hat x. I'm going to put a tilde. What this is, so with respect to the training data, and then there is an expectation of eta hat x, again, with respect to the training data, minus eta of x, the actual eta. So this is called the bias, and the other one is called the variance. So it's the variability with respect to training data. Okay. So intuitively, if you increase edge, the variance goes down because you're averaging over more things. So if you think of this this picture, For H large, this is very wide, and so when you try to average, you average over a lot of training data. And when you average over a lot of training data, the variance goes down. And so you get things that are smoother, but because you're averaging over a lot of things, and those like things that are far away have probably different APEs than the current one, then you would increase your bias. So this would generally go up, and this would go down as you increase H. And the variance sort of like the population level thing or like ensemble thing, but it's manifested as the wiggles. It's not exactly the wiggles are not the variance. You sort of see it in one picture. Yes. Question.
So
Yeah, there. Question. Okay, does make sense. So this is the another kernel which is not smooth. So this is the box. So Gaussian kernel is very smooth. I think it's smooth estimated. This box kernel, just with the box. So instead of these, you would get like a box, 1 and then 0 here. And then you'd get it's like variation in this box. Things like this. This it's not as smooth as a jump discontinuity. And if you do it with this kernel, you'd see it's something like that. It's all the same type of behavior. So this one is like smooth, but still like you can see it stepwise. The other ones are less smooth, and so you can see a similar behavior with this kernel as well. Okay, sounds good. So how do we choose the bandwidth? If you understand what it is now, I need to actually choose the H. Bandwidth selection. It's like one of the classical things. Many pages of statistical literature devoted to choosing the bandwidth.
just a terminology question. So here we have a Gaussian kernel.
Yes.
What is the NW estimate? What is the Nadaraya-Watson mean?
So Nadaraya-Watson means exactly this estimator with K, which is this. So you plug in this particular kernel, translated in a scaled version of like a base kernel into this formula. So basically I've written it here. So this is Nadaraya-Watson.
So Nadaraya-Watson just refers to the continuous derivative of the regression function.
Not the continuous. So it's like this particular estimator of the regression function. This one.
Okay.
Okay. So now parametric estimator of the regression function. It's very similar, close to this, but you also take the translation for the variance, sort of. Okay. It's like obtained by translating the base kernel. So this should be like K naught. So Nadaraya-Watson estimator is like eta hat. X is summation I from 1 to n. K xi minus little x divided by h. Yi divided by summation I from 1 to n. K naught. Xi minus x divided by h. Sounds good. This also works if y is not binary. So this, if you think about it, it's perfectly approximates if y is like real values as well. And in fact, we're going to analyze it in that case. It's easier in the regression. But in the regression case, you can see because y is binary, and you know that these that this is approximating the actual regression function. So the regression function in this case, so remember, generally it's expectation of y given x, but for binary random variable it's the same. It's probably a y for one given x. And probability is between 0 and 1. You'd expect the regression function to be between 0 and 1. And this is a, like, you can also verify that this is going to be always between 0 and 1. And then you can see it here. So it goes like this. It doesn't have to be monotone always. Okay? So if you have a case where so some of the data points that are 0 are here, some are here, and the data points that are 1 are here. If you plot this estimator, it would like go like this, and then come back down. Okay. And then when you threshold it, you get 2 cut points, and then so you classify in between to be anything here would be like 1, anything outside would be 0. Okay, monotonicity is not proper. Okay. Oh, good. Yeah.
What's an estimator is one of kernel density estimation and
No, kernel density estimation usually refers to anyone remembers kernel density estimate? So that goes back to the question of why I have 1 over h here. Okay, so there is a like the companion to this. There's an estimator which is very similar to this, but like estimates the density of x, like P of x that we have today. The kernel density estimate usually refers to that estimator of the density of x itself. There's no y there. Okay, so that estimator is, we have it here. Thought I mentioned it somewhere last time. Yeah, okay, so that's this part. There are no. This thing. It's called kernel density estimate. Okay. Density estimation is like a companion problem. It's not exactly this problem. Density estimation. So an estimator of the, if it was like a discrete variable, if x was discrete, it has a probability mass function, and you can estimate the probability mass function like that. It just counts how many xi's match x and divide by the total number. If you replace this indicator with a similarity measure, it would be like that. And if you replace it with this scaled translated version, it would be that I wrote. That's not kind of density. It's very similar idea to Nadaraya-Watson. Nadaraya-Watson usually used for regression. Like this, the conditional distribution y given y equal 1 given x, or y given x is the expectation, sorry, expectation of y given x. This is for estimating the density of a continuous random variable. And that's where this extra edge comes into play. It's there to make sure that this integrates to 1. Assuming the k naught integrates to 1. Okay, so other question? You don't have any questions? Let's see if someone can answer my question. How do we choose the bandwidth, the edge? Yeah.
So you minimize the MSE.
The MSE. So there's no MSE here because we're doing that. You can do MSE, but we're doing like classification. You can do MSE, but because I'm doing classification, let's say I care about the probability of error. So you can try to minimize the probability of error. How do I do that?
The amount of loss.
The loss, which would be, sorry?
the alternative.
The optimal risk. So the issue is that I don't have, so okay, so going back, risk classifier was like expectation of the loss, depending on, I forgot which way I wrote it, but like, okay, Yeah, maybe like I wrote it like this, f of x and y. In our case, with the 0, 1 loss, it's going to be probability of y, f of x not equal to y. But I don't have this probability. This is unknown. I don't know the joint distribution of x and y. Okay. So I can't calculate the, let's say, optimal, not the optimal, let's say the actual is, or the generalization error. But I talked about this before. So how do we do this? In fact, we can estimate, we can get an input estimate. How do we get a good estimate?
Do you minimize the sum of bias and variance?
So that's related bias square plus variance. That would be the MSE. We'll talk about that in regression, try to do that. But again, if I try to minimize it, I need those distributions because we calculate this and the actual distribution. So there is an optimal value theoretically. So if I know this distribution, it's a good problem actually. So I know P, I can try to minimize H because I can calculate potentially this theoretic base and then there's an optimal H. But in practice, I can't calculate this in the classification. This loss or this probability of error is similar to the MSC variation. We'll talk about MSC. But the MSC has this factorization of variables plus bias squared. We'll talk about it. But they're the same. So trying to minimize the sum of these two. We're trying to minimize this the same, and neither I can do in practice. In theory, I can do. But we're talking about practice. There's one thing like general rule in machine learning.
Plug in.
Plug in. Plug into what?
You mentioned the test error.
Test error. Good. So you need to have a test sample, and then you can just evaluate this. Right, remember there's this R of test, let's say if you want, which is like 1 over m if I have a test sample of size m, indicator f of x tilde I not equal to y tilde I. So I can actually evaluate this. Because you have a test sample, you have your classifier, which is this. You go and apply it to each of the test sample and count how many times you make a mistake divided by the total number. That's your test error. Okay, and then you vary h, you get a different test error. And you plot that as a function of h. And you see where, you don't have to plot it, you can find h, which minimize. Make sense? So you do that, you get a plot like this. So you have the bandwidth. Test is the classification rate for the following 31. You can see it goes down, and it goes back up. And that's the zoomed in version, the right one is the left one. So the other side is the zoomed out version. So if you zoom out, the scale of 0 to 1, it's not 2 centimeter band, but there's an optimal band. If you zoom in, like, the difference is like 0.015, sorry, 0.2 versus about 0.5%. So then you go, so here I'm just varying them in the range, and we're just computing the test error and just plot it. You can see it's like there's a sweet spot. But you can also see it's not too sensitive because of the affected classification. And so you really care about the boundary. You can see it's like so this is where the bandwidth gets large. So this is where things are close. Okay. If it's too large, it's bad, but like moderately large doesn't matter that much. Because I just care about the boundary. It's okay if I make errors here. Okay, so if the regression function is not correct there, I don't care. If it's not correct here, I don't care. If I have a lot of data points around the boundary, then this part is going to be accurate. And I really care about the boundary. Okay, I really need this to be correct. So the x's for which I like close to 1/2. I have to classify those. The thing, what happens is what the derivation function does outside is not of interest or doesn't matter that much. For that reason, in a sense, classification is easier than regression. And this law is like more forgiving than MSE. So MSE cares about what this regression does, function does everywhere. This only cares about like the classification error, and just because of the structure, this only cares about the boundary. But that's what you do in practice. Okay, in practice, the easiest way to choose the boundary is the this is sometimes referred to as hyperparameter tuning in actually both. By statisticians and machine learning people. I have hyperparameter selection, optimization, tuning basically. Actually, the tuning parameter. So this is part of the estimation procedure. So really the test error that we use here is actually, you should be basically the validation set, if you remember. So you shouldn't use your actual test data. So it's part of the training. So you split your training into a piece which we call validation. So it really should be validation. So you have your training data. So there's the test, which I'm not going to touch. And then you have the training. And then you split one part, call it validation set. And so you train on the rest. Train here means just formally classify based on that, what we did. And then you validate it, you compute the error on this. And then you change the boundary, and then you revalidate on this part. And then once you're done, you have your bandwidth. Now your entire classifier depends on this entire training. If you use this part to choose the bandwidth, then you go and test it once on the actual system. Or there's another one that people like in statistics use, which is to do cross-validation. Okay. What is cross-validation?
Take different validation sets.
You take different validations. So the issue with this is that I'm just using this part of the data to validate. But what I can do is that I can like train on this part, basically form the classifier, the one that we did. And this part validate on this, and then you do a different split. You train on a different split and then validate and repeat this process many times, and you take the average. And in practice, what they do is they do k-fold cross-validation. So k-fold alternatively. Do k-fold cross-validation, which is to say, let's say with k equals to 3, say k is equal to 3. What I'm going to do is break this data into 3 pieces. Okay. First, I'm going to take this as training, and the last piece as test. Then I'm going to do the middle piece as like validation, and the other piece is training. And then last, I'm going to do this. This is going to be validation. The rest is going to be training. So every time, so the classifiers change because you're training or like using different training data. But what I really care about is a good approximation of the risk, in a sense, or like the good bandwidth. So this way, I'm training on every portion of the data and test on every portion of the data. Hopefully, you get a better estimate once you average. So there are like attempts in like literature to try to say, okay, this is a good estimator of the risk. There is issues because they're dependent, so it's hard. So what if you do it once, these pieces are independent. And once I do multiple times, everything is dependent and averaging over dependent things. But intuitively, this is a good estimator of the risk. And then you plot this as a function of h, or you evaluate as a function of h, and then you choose it. Yeah.
So for one of the splits, we get a curve, right?
Yes.
and then we select the H.
Yes, if you just want to do one.
So if K equal to 3, we have 3 different H stars.
So no, that's not what you do. In this case, you just compute for every edge, you compute the average of the risk. You just sort it at one plot. You get a better plot. Right? So you don't do different plots for these. So you evaluate the risk, right? And then you have the plot, you can give the plot for the average of plots. For each one, you get a like fixed edge. You get an estimate of the risk as a validation. Yeah, you get another one, you take out one or two, some of the alt. So that's another estimate of the risk. Hopefully a better estimate.
So basically, we have 3 curves, and the average of the 3 curves is another curve, and we
Yes.
take H star of that.
Yes,
that
yes,
curve.
yes.
And then using that H star, we report our test result.
Yes, yeah. So that edge would be your, like, defines your actual estimate for like that stuff. Then you report it.
What's the advantage?
Sorry?
Why do we have to do this? Validation?
So why do we have, so you tell me, why are we doing the validation? We will have to choose the bandwidth.
Yeah, I mean, why do we have to do it 3 times?
You can do it 5 times if you want.
I mean, why do we
You
do
don't
it?
have to do 3, yeah. You can do K4. Like 3, 5, okay. But why do you need to do cross validation?
Yeah.
Because these are all estimates, right? So if you do it like this, for example, it could be that when you split, there are outliers in this part, and like it's going to be variable. If there's maybe more variance, more sensitive. But once you do it, in practice, if you just validate like this, and this is large, it's a good estimate of it. I think what I'm doing here is one step. You don't necessarily need to do cross validation. But statisticians like talk a lot about this particular procedure. Like if you use all the data once for training and once for validation, because you sort of think if I use all my data for doing this, probably I'm going to do slightly better, maybe better. Right? Does it make sense? So in this way, everything goes into training and test once for like validation. This way, like just randomly, one goes to training, one to test. It's not necessarily clear that it's going to matter much, especially if your data is uniform. But if your data has outliers, and by chance this validations have outliers, then things are going to be like thrown out. So this is going to ultimately avoid that.
Theoretically prove that this is better now.
That's a different story. Whether you can theoretically prove it or not, I'm not sure. In various like specific setting, people look at this. But if you're interested, look into the literature and let me know. And it has anyone proved that doing this is necessarily better? I'm not sure. You can try to prove that this is consistent. But whether it does better than, and then also the K matters. So what should be now you have a K. So it should actually 2-fold, 3-fold, 5-fold. The issue is like once you increase K, the smaller the sample is, then you get more variability here. And when my validations is smaller, anytime you're like estimating based on a small sample, you get more variable. But then you have more, the average is more and more. So it's not clear. It's like complicated dependence on K. But let's not worry about the period. It's an interesting question. Short answer, I don't know. Right, like, okay, what I want is better than that. Intuitively, it should be better. The advantage of this is not like it's like a single classifier. Here, when you do it, then you have different classifiers. That makes it complicated to analyze. Questions? So this procedure you can do like more generally for any method that has a tuning parameter, or you have like something that you need to determine. Okay. Here it's just the bandwidth. but in like some models, there's some other parameter, like the number of layers of a neural network or whatnot. You can do this. Sounds good? That's fine. Yeah.
For the two parts, it's just used to reference on the testing part, so.
Based on the validation, let's see, the two plots are the same, just zooming in. Yeah, so here, applying the validation there, is split the training into one part validation, one part the actual training. The training on this, basically, eta hat is something here, and then you test on it.
And then you would just want to just like the lowest.
Yes, choose the bandwidth that's small. You don't have to even plot it, you can just like compute them and choose. So you usually you do, but this is something called grid search as well. Grid search. So you have a range of bandwidth, potential bandwidth. Let's say I'm going to choose from 0, 1, 0 to like maybe 10. Okay, and you have to split this interval into like a certain set of points. Let's say I just check this maybe 0.05, maybe 1, 2, maybe 5, and 10. Scale with like logarithm or something. So just check these like 6 values for bandwidth, compute the test error, and then choose the one that has the smallest.
Do you mind explaining that, how the training validation with the test set work?
Right. So the thing is, you want to use your estimate of the risk or estimate of the generalization error. These are the same thing. And that is done by breaking off a sample which is independent of your training data, right? And then train the test on that. Okay. So the reason why I'm doing this 3-layer split is that in this case, I'm using this part of the data to actually optimize the classifier itself. Okay, so the bandwidth is part of the classifier. So you have this, you can think of it as I have f hat of h, which is 1 if I'm going to write that eta hat h of x bigger than 1/2, eta hat h of x less than 1/2. And so what you really have is this is a family of classifiers indexed by this bandwidth, and I need to choose this bandwidth. In the end, what I have an h hat here, the h hat, that will be my final classifier. Okay, so this h hat that I'm going to choose, if I'm going to use this part of the data, the test data to choose it, this also went into the training nodes. The training is like formation of the classifier. Okay, then this is effectively would be my training data. It doesn't make sense to test on it because I chose the specifically optimized variables. So for that reason, I'm going to take my training, like test is going to be like completely separate. This is for testing this one's final, like the final estimate. So you take the site because I'm like choosing it is part of the training classifier, and just like this part, that's what we get into validation that to make it independent of the rest. Then I form my classifier based on this, test on this, and vary edge. Now I have it with, because the training data and this are also independent. Okay, so when I evaluate this classifier and this, I get a good estimate of the risk because of the independence. And I vary edge. For each one, I get a good estimate. And then I go to the right one, and then I plug in. So final estimator. So let's say family of estimator. Family of estimators. And then the final one is f hat of h hat of x, where h hat is obtained by minimizing validation error. Okay, so that's my final classifier. So this h hat will depend on both the training and validation. F hat depends on this part. So in the end, this entire thing depends on this entire thing, but it's independent of the test. So now, one last time I tested that. And that's my final prediction of what it does to train. So like, unknown population.
So the Y is really for the validation.
Yeah, what?
So the Y-axis of the plot is really the validation setup for the.
Yes, validation there, yes. So this is, I should, yeah. So I mentioned I usually don't mix validation and tests because we usually don't have an extra test data. But yeah, if you want to be precise, this is validation. Validation. You can think of the test as someone else holds the test data for us. We have no access to it. So that's why I say training test, but I should probably be more precise for the testing. Sound good? Everyone understands what we do the previous split, basically. Okay.
But we also not change the test,
The what?
like there are 3 validations.
Oh, do that differences for the test. That's what you can do, but in practice, again, people just usually have like a particular test set that they use, because that would complicate, because you have to output like multiple classifiers. So let's say you have a competition, if I have multiple test data, then I have to, or it's harder because I guess some people do it in practice. So you have, I'm not sure if they do it, but yeah, I think some people, as long as you're consistent in how you split, let's say if you want to compare with someone else, right? You want your splits to be the same, right? So you say, I'm going to train on this, test on that, and then train on this, test on that thing, and then everyone will do that, and then report the average. That's doable. But there are complications, because if you start doing this, then you tend to end up like overfitting probably to your test as well. It's hard to say, but potentially you can do it. Potentially you can do it, but it should be easier.
We want the test data to be representative of the entire data array.
Yes, yes.
So if you only split one slice of it, it might not be the representation of the.
Right, the same issue happens here, but as I mentioned, if you do it randomly and the data is sort of uniform, not uniform, but even if you have heterogeneity, if you do enough, you hit each part of the population once. This would be good enough. I don't remember if people necessarily do this. Some people I think do it. People might like see, but both are common in practice. The cases where people have competitions, usually you have a single test. They hold part of the data, and then you just train on this. You can do whatever you want here, and then they test it for you. But when people have their own data, or just the data is there, you can do multiple splits. But then you have to be consistent. Everyone has to use the same splits. Otherwise, it's like not fair. But statistically, if you think about it, once you have enough samples, if you do randomly, then this should be representative of the entire.
The same thing, I can use the same argument for validation, right? I can randomly
Yes.
sample from my training data.
Yes, yes. So that's why I said it's not necessarily clear if this is going to be better than case one. Yes. Once it's, so you can see I'm doing once here, it's fine. Right. Yeah, so that's like a very like I would say fine detail of whether it matters to do with multiple splits. That's validation done. Once this validation data is like big enough, it should match. When it's very small, so this often matters if your data is very small. Okay. Once I got to split, then I don't get a good size up. So statisticians traditionally thought about that data scarcity, the situation where like you have like maybe 50 samples. So you want to like extract all the potential information. If you're doing machine learning, the data is like 10 to the 12, like trillions of like billions of everything. The data abundance setting. So you don't worry too much. Sounds good. We can try to like teach an entire course in class validation, and I would prepare for that course differently. But let's say don't worry too much about it. Any other questions? Okay. So if not, so let's I'm going to come back to the theory of this in the regression context. But to do the theory and also in practice, there are other variants of this local averaging which is of interest. So if you remember, this local averaging was, I wrote it a little bit more generally than the Nadaraya-Watson. So if you have a similarity metric, this is your local averaging. This doesn't have a particular name. I'm going to call it local averaging because it's what it is. Or similarity averaging if you want. Local averaging. Or better, like similarity averaging. One example of this similarity metric is if I'm assuming, let me do it in the 2 dimensions. Do I have there? What I can do is I can partition the space into like fixed portions. Okay, this is the easiest way to make a similarity metric. And then say I'm going to say that 2 data points are similar. Let's say xi is similar to x if they're in the same cell of the partition. Okay. This is this similarity matrix. So k xix is 1 if xi and x are in the same cell. This cannot be written in the translation variant case, but the idea is very similar to the previous. Okay, 1 in the same cell, 0 other one. Okay, so this has the effect that I'm gonna only, for this x, I'm gonna only average the y's for the data points whose x lies in this cell. Okay, so this is the easiest like estimator to analyze, and this is what we're gonna analyze for the dissect. It's very similar to the box kernel, Nadaraya-Watson with box kernel, but Nadaraya-Watson with box kernel, what it does is that it puts a box around x. The difference here is that the partitions or the lines are fixed ahead of the time. That one is like dynamic. So at x, if I have an x, I'm going to put a rectangle around it of side length edge. This way is slightly different, but it's much easier to analyze this one. So here you still have probably like side length edge here as well. And so the bandwidth would be this side length of the diameter. Yeah, so. Okay. What I'm going to do often is I'm going to call, so the cell of the partition that contains a particular x, I'm going to write it as a of x. Okay, so we have a test point x. The cell would be a of x, so I can write this estimator as a hat of x. So this is going to be an indicator that xi belongs to a of x. Then my estimator would be summation. Yi and then divided by summation. So this one, we're going to come back and analyze in the context of regression, actually. Okay, there is this one, and then another one, which is very popular, which falls within this category. So this is partitioning. The other one is the k-nearest neighbor. K-nearest neighbor estimator. This one has k of xi and x is 1 if xi is among the k nearest neighbors of little x. So I go look at the little x. Look at my training data, all the training points for which xi is the k nearest to little x among all the ones. So like the simplest one is the one nearest neighbor. So you go look at xi, look at all your training data, the xi that's closest. You take the y of that. There's no average. The one nearest neighbor is a very like simple estimate. It's essentially similar like to the one that we did for the discrete case, where you just took the yi of the like you average over all the yi's to x is exactly equal to x your little x here. You just take the yi of the particular xi that's needs to go average, or you can do like 3 years data or like 2 years. K is smaller than it. Okay. So we're out of time. Next time we'll come back hopefully and talk about these two estimators, mostly about the partitioning estimator and trying to analyze and see that bias variance trade-offs in theory. Okay. Thank you. See you next time.